Okay, here we go. 11. Okay, first big thing. Read slow on the AP test. If you read quick, you're going to miss a question. Like they put the wording in such a way that if you read fast, your brain will say, oh, I've read this before, and it's this, and it's not. So read slow. The function f is defined. Okay, don't make the assumption that this is f. That's a mistake people make all the time. It didn't say this is f. It just says f is defined on the interval 0 to 8. It still didn't say this was f. Don't make the mistake. This is not f. The graph of its derivative, so f's derivative is up here. This is f prime. Y'all with me? They labeled it and everything, but sometimes they don't label it. Like you just have to make sure you read carefully. So that's f prime. It says how many points of inflection does the graph of f have? So they're asking you a question about a graph you cannot see. We do not have a picture of f. We don't know what that is. All we have is a picture of f prime. Questions so far? Awesome. Okay. I don't recall if in a previous class they ever mentioned the word inflection point. I'm just curious, not if they said inflection point. Shake your head if you don't. That word is new to you. This looks pretty new. Okay, so on your reference sheet, there's a definition you're going to have to memorize then. The reference sheet has a box that looks something pretty similar to this. It says, any function has an inflection point when that function changes concavity, meaning concave up to concave down or vice versa. So any function has an inflection point when that function changes concavity. You must memorize that sentence. Yeah, please, Conrad.
Are we going to need to know, like say I had a graph that went up and then down, do we need to know the specific point that it switches? Or do we just need to know that there is a point there where it will switch and it is an inflection point?
Awesome. From a graph, they will only expect that you can identify the general area where the inflection point occurs, not the precise location unless they give you some additional information. So close enough, yes?
Is that the same thing with the slope as well?
From a graph, you're not expected to do anything precisely, just general idea, unless they give extra information that helps. So the best thing I can tell you is even though they're setting lots of traps for you, they are never setting an unfair trap. Unfair would be, tell from the graph like what this number is, and it's like, how am I supposed to know? There's just no way to know. They won't do that to you. It'll be clearly obvious, or there'll be extra information to help. So, some more for Spencer. Anybody else? Two for Conrad. Okay, cool. Okay, we're looking for an inflection point on f, but again, we cannot see f. We don't know what f looks like. So what we do is we use a little tool that was created by a student of mine about, 20 years ago. Her name was Danica Wright. I have had relatives of Danica in class periodically. So if it's a relative, feel free to let me know. I'll get very excited. She put together like what I had taught her in a very compact and easy to remember way. She created this little chart, and I asked her if I could use it in subsequent years. She said yes. Now she's pretty famous in my class. I talk about her every single year. Her picture is on her chart is on the wall. Some other student made that and gave it to me as a gift. So it's on your reference sheet in the top left corner. It's not quite as complicated as this version, but it's roughly the same idea. And here's how I use it. You have memorized that f has an inflection point whenever f changes concavity. So you're looking to see when this will occur right here. When will f change concavity? You're trying to figure that out, and you don't get to look at f. So we're not looking at f, we want to figure out when f changes concavity. Well, Danica's chart says that, hey look, f changes concavity at exactly the same x-coordinate where f's derivative changes from increase to decrease or vice versa? That's because when f is concave up, that literally means the slopes of f are increasing. When f is concave down, that literally means the slopes of f are decreasing. So we're going to figure out where f is changing concavity by figuring out where f prime changes increase to decrease or vice versa. Conrad, please.
Will we ever have to find inflection points of f prime from f?
From f? No. I have to think about that, whether it's even possible. So if I know the answer is no, I'd have to dig in a little further. So no for now. Anybody else? Okay, so back to the picture. So we've got our picture of f prime. For example, here, I'm going to call out some people's names. Let's try Blake. This is f prime. Right here, Blake. Is that slope positive or negative?
Positive.
Cool. 2 points. Let's go to Noah. This one here, Noah.
Positive.
Positive. More positive or less positive?
Less positive.
Less positive. 2 for Noah. So this is f prime. And along here, f prime is concave down. Because the slopes of f are decreasing. We come up here, the slope of f is 0. And then the slope of f becomes negative, f prime. Slope of f prime becomes negative. So all along here, f prime is concave down. Because the slopes of f prime are decreasing. That's what concave up and concave down mean. It's right here on the chart. Excuse me. If f prime is concave down, then f double prime, which means the slopes of f prime, would have decreasing values. So this f prime section is concave down. You have a flaw on your reference sheet, there's a typo. This D on your reference sheet says I. Make sure you change that to D. Okay, so this graph of f prime would have an inflection point right about here. Back to what I said to Conrad and Spencer, you would kind of guess about x equal 1.5, but it's not necessarily perfect, it's just that vicinity. That's when f prime has an inflection point. Because after that, the slopes of f prime are increasing, and this section of f prime is now concave up. But that's f prime. That's identifying an inflection point on f prime. We are not trying to find an inflection point on f prime, we're trying to find an inflection point on f. Questions about anything? So even though f prime has an inflection point right here at x equal 1.5, that is not where f itself has an inflection point. F has an inflection point when the concavity of f changes. We don't have f to look at, so we look at f prime instead. When f prime changes in this manner, that's when f will have an inflection point. So raise your hand if you can guess at approximately what x does f have an inflection point. Hands up. Approximately what x value will f have an inflection point? Pretty good, most everybody. Let's go, Cora.
6.
So x equals 6. 2 points for Cora. The mistake you're making, no big deal, is that this is a graph of f prime, and right at x equals 6, it does appear that f prime is changing from concave down to concave up. That would be a place where f itself would have an inflection point. I said that badly. That's where f prime would have an inflection point. So when f prime changed concavity, that's where f prime has an inflection point. That's not where f has an inflection point. F has an inflection point when f prime does this. So hands up, who knows where f has an inflection point? Where does f have an inflection point? Better, let's go, Sam.
1.
At x equal 1, f prime is changing from y values that go up which means the slope of f is increasing, to y values that go down, which would mean the slope of f is now decreasing. When the slope of f is increasing, that's when f itself is concave up. When the slope of f is decreasing, that's when f itself is concave down. So f changed concavity at x equal 1. We don't see the graph of f, but whatever the graph of f is, it's going to change concavity at x equal 1. The graph we're looking at did not change concavity at x equal 1. 1 second. We'll go to Paisley and then Cora. So all A's over here, all A's over here. Okay, you've got to force yourself to be super detail oriented. As we talk about all these ideas, you got to make sure you say this a lot so I can tell what graph are you speaking of. You've got to make sure you address the graph you're talking about over and over again. Otherwise, you get mixed up as to which graph we're talking about. Let's try Cora, please.
So why wouldn't there be like an inflection? Or wait, no. I just don't understand why it would be 1. Like.
Do the one you were going to ask a minute ago. I like that better.
Wait, what was it?
You were going to ask something else. Do that first.
An inflection point. Is there an inflection
You
point?
said, why wouldn't there be?
Like, why wouldn't 3 be whatever 1 was? Was 1 when it changed cavity?
Let's say it back to
Cavity?
you. So what you really want to say is, does, and now you have to tell me f or f prime. Does,
F prime.
okay, so you want to say, does f prime, come on, Pen. Does f prime,
Change.
doing great, bunch of points coming your way. Change what?
Concavity
Perfect. Does f prime change concavity?
at x equals 3.
Perfectly stated. 5 for Cora. No, that was very good, just being patient. Look, everybody's going to answer it. Say it out loud as a class. We are looking at a graph of, that's why there's a sign here, so I can remind you to say it over and over again. We're looking at a graph of what? Say it. F prime. Okay. The definition is any function. Just say yes or no. Is f prime a function, yes or no?
Yes.
Yes. So this could say f prime. Any function, f prime, has an inflection point when that function, so that function is referring to what? Say it. F prime. So f prime has an inflection point when f prime changes concavity. So go to Cora's question. Here's a graph of f prime. Now this might help as well. Okay, teachers do this all, 1 second, Conrad. Teachers do this in a lot of different ways. This is the way I think is best. If a graph has this shape or any portion of it, that graph is concave up. If this graph has this shape or any portion of it, concave down. So raise your hand. Actually, just say it out loud when I prompt you. This little section of f right here, that little yellow section, concave down, sorry, this little section of f prime, concave down or concave up? Say it. Good, concave down. It's this portion here. Okay, now I'm not trying to trick you, I just want to hear it. This little section of f prime, concave down or concave up? Say it.
Concave down.
Perfect. So just say yes or no. At x equal 3, did f prime's concavity change? Yes or no? Say it. No. So x equal 3 is not, does f prime change concavity at x equal 3? No. F prime does not change concavity there. Okay, but there's a connection that they're trying to get you to see. The connection is nicely illustrated in Danica Wright's chart. She figured it all out. She says, oh, wait a minute, though. F prime can change in a different way. F prime did not change concavity at x equal 3. F prime did change in a different way at x equal 3. Hands up, who knows? How did f prime change at x equal 3? There we go. How did f prime change at x equal 3, Cooper?
It was increasing and then decreasing.
So f prime was going up. Now f prime is going down. How many saw that? Two more. When f prime changes increase to decrease, I'm not trying to trick you, just say yes or no. When f prime changes increase to decrease, does that mean f prime has an inflection point? Yes or no?
No.
No. Means f prime changed increase to decrease. F prime has what's known as a relative extrema and relative max. But f will have an inflection point. We can't see f. If we could, we'd see f changing concavity. That's what Danica Wright's chart is telling us. Let's go to Conrad.
I have two questions.
Please.
For one, so the inflection point definition of any function has an inflection point. Does that mean that an equation that like broke the function rule, even if it ended up concaving at some point, that will not have inflection points because it's not a function?
Oh, excellent. I really should have said any function or relation can have a function inflection point. So that's my bad. Keep going.
And then, so for when f concave up, concave down inflection point, f prime is when it's increasing or decreasing for f. F double prime when it increases or decreases, is that the inflection point of f prime?
Perfect. Two more. Once you understand, look. It's really pretty simple. Once you understand how f relates to f prime, there's nothing new to learn. F prime relates to f double prime in exactly the same way, no exceptions. There's no difference. F double prime is the slopes of f prime, so they relate in exactly the same way that f prime relates to f. Let's go Paisley, please.
So I'm just kind of confused on what the difference of the positive and negative and increasing and decreasing is. Like, what's the difference between those two?
Oh, awesome. So when I say, let's do it together, two for Paisley. Just say it out loud for a minute. This is f prime. Right here, say it out loud. Is f prime positive or negative? Say it.
Positive.
Along here, is f prime increasing or decreasing?
Increasing.
Increasing. Right here, is f prime positive or negative?
Positive.
Is f prime increasing or decreasing?
Decreasing.
Decreasing.
So is it like with the slope, like when you're looking at more of like a, like when it's a point, it's positive and then,
Oh, positive and negative is simply the y value.
okay.
So all of these points are positive y values, but those y values are going up and down.
Okay, that makes more sense.
And simultaneously, the slopes you're looking at are also changing from positive to negative.
So when it's on the other side, like
Yeah,
it's the
like
second
right here.
one, okay, that makes sense.
This is where f prime is negative.
Okay, that makes sense.
But the part, you'll get good at it quickly. This is not, everybody gets good at this. There's positive and negative, increasing and decreasing, concave up, concave down. We've got to keep track of all of those. And within that, we've got to keep track of, are we talking about y coordinates, or are we talking about slopes? Like right here, say it together, is the y coordinate positive or negative? Say it.
Positive.
Right here is the y coordinate positive or negative? Positive. Right here is the slope positive or negative?
Positive.
Is the slope right here positive or negative?
Negative.
Negative. Are the slopes along here increasing or decreasing?
Increasing.
So that was a problem. The slopes along here are doing this. They are positive, but they're getting less positive.
So would that be, like for the graph, would you consider that decreasing?
So that, I gotta say it back to you more carefully. This is a graph of f prime. In this section right here, every slope of f prime is positive, but the slopes as a whole are decreasing little by little. They're becoming less and less positive. Along here, the slopes of f are negative, and they're becoming more and more negative. So along here, the slopes of f prime are negative, and they're becoming more negative, meaning they're still decreasing. So that's what we're trying to get you good at doing.
So like
Right,
for the
yes.
first one, even though it's still going up and like the number is like getting a little bit bigger each time, just because it's getting like increasingly like less bigger, Does that make sense? That means it's decreasing?
What you got to keep working on is throwing more words. More words. What you really meant to say was this. This is f prime, and those green values of f prime are all positive, and those green values of f prime are all increasing, because they're the y values.
Yeah.
If we now look at the slopes of f prime, because those y values get bigger and bigger, slower and slower, the slope or rate of change of f prime is decreasing. So the slopes of f prime are decreasing. The values of f prime are increasing. That's what's happening.
Okay.
And what makes it even one step further more complicated is because the values of f prime are all positive, the slopes of f prime are decreasing, but the values of f would be increasing. Can't see f, but that's what they'd be doing. So help a little bit. Two more, Cora.
Okay, so this is kind of back to the question I was asking earlier, but we did something, and I might have been like zoned out. I just didn't stick
You're
with
fine.
me at all. So at x equals 1 on f prime, is that what's happening there? Is that changing concavity, or is that an inflection point?
So at x equal 1, f prime changes, hands up everybody, 2 for Cora. How is f prime changing at x equal 1? Come on, answer. Hands. How is f prime changing at x equal 1? How is f prime changing at x equal 1? Let's go over to Sophia.
It's going from positive to negative.
Not quite. Let me kind of help you see your mistake. This is f prime. The values of f prime are all positive. So the values of f prime
it's
are
going from increasing to decreasing.
much better. The values of f prime change from increase to decrease at x equal 1. So f prime changes, increase to decrease, 2 for Sophia, at x equal 1. Be honest, how many knew that? Come on, hands, show me. Doing pretty good. 2 more. So that's what's happening at x equal 1. Say yes or no. Does that mean f prime changed concavity at x equal 1? Yes or no? No. It means f prime changed increase to decrease. But it does mean the unseen graph of f did something at x equal 1. What did the unseen graph of x do? F changed concavity. Because we are observing f prime doing this, which means we know f did that. That's the idea. Okay, hands up again. Where else does f change concavity? Hands, come on. Where's the next x coordinate where f changes concavity? The boss Sam, he's really tired. He's still asleep. We'll let him rest for a moment before we disturb his slumber. Let's go, Carter. Carter's like smiling because he's been in the same boat. Carter, where is the next x coordinate where f changes concavity?
Just f prime.
So you're doing great. The pausing was the perfect thing to do. You've got to make sure you know the question or they'll trap you. What is the next x coordinate? We're looking at f prime. But I want you to tell me what's the next x where f changes concavity. 2.5. That's a spot where f prime changes concavity, not f.
Oh, sorry.
Because that would be f prime doing, so here's f prime being concave up.
So that'll be 2.
That's better. Here's f prime being concave down. X equal 2.5 is about where f prime changes concavity.
Okay.
F itself changes concavity at x equal 2. When f prime changes decrease to increase. How many knew that one? Show me. 2 more. Okay. Oh, there, Samuel's back. Kind of. Anybody else? I'm making a video of this, Samuel, so you can go back and watch the video to help with whatever you missed.
Thank you.
Okay. Pretty good. Okay, hands up. We know f changes concavity at x equal 1 and x equal 2. We so far know that f prime changes concavity at about x equal 1.5 and x equal 2.5. Madeline, please. Oh, you're just waiting. You're good. Pretty good. Questions, anybody? So just checking, where's the next x where f prime would change concavity? Hands up. Madeline, please. About 3.5. So right here, that's where f prime is changing concavity, not f. How many knew that one? 2 more. What is the last x where f prime changes concavity? Hands up. What's the last x where f prime Benson changes concavity?
4.5.
So 4.5 is a good answer. There's one more right here.
Oh, wow. Oh, yeah.
No worries, that makes sense.
Yeah.
So the last place where f prime changed concavity was x equals 6. How many knew? 2 more. We have a question. What's the last x where f changes concavity? Hands up. What's the last x where f changes concavity? Isaac.
Is it 7?
Who votes 7? 2 more. So hands up. What's the correct answer to this question? Hands. I hope I've done a reasonable job of showing you how they can try to fool you. But once you understand the idea, they can't fool you. Sienna.
6.
Sienna votes 6. How many are voting 6? 2 more. Cool. Questions, anybody?
I was just looking at it first.
Oh, you're good. Keep looking. Keep looking. Can I erase? Okay, last question. Another way they might ask the question is they might say this is a graph of f double prime. So they might say this is f double prime. And they might say, where does f have a point of inflection? Danica's chart makes it really easy. Because if the slopes of f are increasing, that means the rate at which f prime is changing has to be positive. If the slopes of f are decreasing, that means the rate at which f prime is changing has to be negative. And it goes all the way back to f. So f changes concavity when f prime does this, or when f double prime does this. So hands up, who can tell me an x-coordinate where f, like if this is a graph of f double prime now, we change the problem completely. If that's f double prime, does f ever change concavity? And if yes, where? Hands up. If that's f double prime, does f ever change concavity, Macy?
Is it at x equals 6?
Nicely done. How many knew that? 2 more. 3 for Macy. 3 for Macy. That's good. Look, we've done a bunch of different things. Summarizing, we said if this is a graph of f prime, how many inflection points would f prime have? Count them and raise your hand. If it's a graph of f prime, how many inflection points would f prime have? It's a graph of f prime, how many inflection points would f prime have? There we go. If this is a graph of f prime, how many inflection points would f prime have? Let's go read.
5.
So if I'm looking at f prime, I would say f prime is concave down. Stop. Now f prime is concave up. Back to concave down. Back to concave up. Back to concave down. It's kind of boring. Finally concave up. So that means f prime would have 1, 2, 3, 4, 5. How many were voting 5? 2 more. 5 points of inflection. We already know that if this is f prime, and we're looking for how many times f has a point of inflection, the correct answer would have been 6. Okay. If this is f double prime, that would mean f would only have 1 point of inflection at x equals 6. Please.
Would they ever give you a question like if this was f double prime, like where would be like points of inflection be for f prime?
Sure, let's do it right now. 2 more for Sophia. Hands up. Just name the first place. If this is f double prime, tell me the first x coordinate where f prime would have a point of inflection. What is the first x coordinate where f prime will have a point of inflection? Only about half of you. This is exactly what happens on the test. They just keep throwing stuff at you that's always new. Isaac.
Is it 1.5?
So 1.5, 2 points for Isaac. That would be where f double prime would have a point of inflection. Because if this is a graph of f double prime would be changing concavity at about x equal 1.5. Hands up again. Sophia's question was, if this is f double prime, where does f prime have a point of inflection? There we go. Let's report it. At x equal 1. At x equal 1, f double prime is changing, increase to decrease. When f double prime changes increase to decrease, f prime's changing concavity. How many saw that? 2 more. That's your question, Sophia.
Yeah.
Okay. Please.
Is there such a thing as an f triple prime?
So it's totally relative. So you can go, like I could have started the whole discussion by saying, we are going to discuss f triple prime. Like we're going to talk about f, we're going to say, hey,
It eats itself.
it doesn't matter, yeah. Like it really doesn't matter. Like, I did that badly, Jackson, give me one more chance. We could have said the function f triple prime is defined on the closed interval. The graph of its derivative, which would be f quadruple prime, is shown. And our analysis is exactly the same. This becomes triple prime. This becomes quadruple prime.
Okay.
Because it's completely relative to each other. Does that answer your question?
Same rules as the thing.
Same rule. They don't change at all. It's all relative. 2 more. Please, Conrad.
Is there any pattern in graphs as you go about the primes?
For polynomials, yes. For some trigonometric functions, yes. But to me, the patterns are infrequent enough, I don't ever emphasize them. But if you see one and ask me, I'll tell you yes or no. So 2 more.
Is there ever going to be a question that's going to be f quadruple prime, asking about just f?
Yes. It's not super common.
Okay.
2 more for Cora. It's not super common. It's not hard. You just remember that you just keep going. Please, because what it is, Cora, look right here. It's just a staircase. There's that, and then it repeats. Just like there's that, and then it repeats. So it's just a big staircase. You can draw the chart out forever. 2 more. Yeah. Oh, please.
I'm sorry, may I use the restroom?
Yes. I'm typing your number here, Sam.
No, my sister got headache downstairs. Been there.
Yeah, Jackson, please.
So you would only use the very bottom bar of that,
She got headache. Yeah, that's
of that, on this chart, if it was a question in relation to f prime to f double prime. Okay.
Yep. To be strictly honest, hey, I always try to be straight with you. I don't know that I ever use this on an AP question. I put it there to emphasize that in case they do, you can keep going, but I don't think I've ever had to. So was there a question, forgot who asked, was there a question that was f versus f quadruple prime? Yes, I do remember that one. Did it involve Danica's chart? It didn't. It was something else. And also very rare.
Okay.
And nothing, it really is nothing to worry about because the pattern just keeps going. So.
Sorry, I'm just wondering, what did you guys, like, how did you teach it without Danica's chart?
So what I did is what was taught to me, 2 more for Sophia. I just wrote lots of sentences like this, which does work. And what Danica did is she got so good at understanding the sentences, she's like, hey, I see a pattern here, I'm going to use it. And she created her own little table to just help her keep track of the pattern. So this, I think, is a great tool because it simplifies a lot of words very quickly. and it just makes it a lot faster. So you'll see me stop using this pretty much entirely and just use this. Question, anything else? Really good discussion. Let's stop the video.